Okay, good day, good afternoon. Today is the last part of the workshop of the notebook for Qiskit events that we have been running is for a couple of days now. Going to be looking at the third notebook whereby we are going to talk about the basic of those aspects in the notebook. So from there, our lecturer is around that's going to be taking us through it. But before we go through it, I will want us to have at the back of our mind that we need to keep on learning this. Is something that you we need to do consistently. It's not just that you learn this and you just forget about it. Is an important aspect. Is a things that you just have to keep practicing so that you can have more understanding. And to this area of to learn and the paths that you are being taken on. So so that will not take much of our time, I would like to call Mr. Sam, who's going to be taking us today. He's just going to take us through. Before that, I would love to share my screen and so that we can see how it's going to go through. I don't know. Can you see my screen, please? Still loading. Okay.
Yes, it's showing. It's showing.
I hope you can see my screen. Okay. Okay. Good. So today we are dealing with this last part, the transpiler. So we are going to be looking at what transpiler is, and from there we are going to have more. Sorry, we're going to have more knowledge. Um, but what I just want us to have at the back of our mind is all these exercise is very important. We go through this exercise. We are the one we we the students are the ones to go through it. We are just going to put you through. Try your best with this exercise. Have the basic knowledge of this exercise. I just answer a few of them, but it's, the basic thing is you people should try it. And from there, for you to understand transpiler, you have to go. You have a document. We have the documentation of its introduction to transpilation. So you go through it, try to read. These are, if you check the notebook, you can see the same thing, but the question may be different. The question is different. Actually, there is no question here. They just explain the stages that you need to follow to create it. If actually I wrote some notes down here how to go through it, how to start the first step, the second step. The first step is your library, you import your library. The second step, you do your what quantum sockets. How many sockets do you how many quantum do you have? Two qubits or three qubits or four qubits are you using? Or so you start with that, and also the transpiler socket. Yeah, but you have to work with the back end. We call the back end, and also if you can see very well, you can see how we call the transpiler socket. Whereby we call our variable of quantum socket, we call the backend, and we call the optimization level. Our optimization level is 3. So we ask it to display. So actually there are conditions here about on this. Also, you can just go through it from the documentation to have your basic knowledge and understanding of that. So I will stop sharing so that our instructors can take over and is going to put us through the necessary things that that we need to do. So, Mr. Sam, Mr. Sam.
Yeah, yes. Thank you very much, Mr. Shegun.
Okay,
I'm with you,
okay.
sir.
Take the floor. Thank you. You can take the floor now.
All right. All right, sir. All right, sir. Okay. Good day. Good afternoon from this side of the divide. In Nigeria, it's an afternoon. Okay. All right. This today being our last days for the Qiskit program, the Qiskit fifth for events. Today we're going to be looking at the last, with the third, which is the last lap of the events of the Qiskit 4. And today, which is majorly on the transpiler, uh, on the transpiler. I'll be sharing my screen shortly. First, before sharing the what's the name? Before sharing the lab work, I would quickly like to give us a background overview of what is a transpiler, and so that we can once we establish the foundation, then we proceed to the just looking at the lab together. Okay, let me share my screen from here. Okay, so let me share my screen. Sorry, minutes. Sorry, okay. Can we all see the screen?
Yes, you can see it.
Can we all see?
Yes.
All right. Oh, sorry, please, but just I have a PDF here, actually just a foundational knowledge about what transpiler is. I want us to just look at what transpiler is before going into the lab itself. Okay, in Qiskit, transpiler is a crucial tool that converts a quantum socket into a form that can be executed on a specific quantum hardware, You know, when you write your code in an IDE, whether it's on the Google Colabs or Grid, either of any development environments, you write a, a, a quantum syntax, quantum program. So if you are not running with a simulator, even if if you are not running with a simulator now, you are running with a primitive. I believe we get like you understand runtime simulators, and I want to assume, because like I know this would have been taken care of in the first lab. Okay, when you are working with an actual quantum computers, with an actual quantum computer, once you have typed your instructions, your socket, you have designed your socket, you pass the information to the backend, to the target backend of the quantum computers. The way, okay, and transpiler is the one that we arrange, is a process of the process of sending the prepared sockets in our ID, in our the development environment that we have prepared. We have written a quantum code, and once a process of sending it in a way that is compatible to with the back end of the quantum computer, the process of sending it to so that will be conformable with the back end of in particular Qiskit IBM quantum computer that will be compatible to it. The process is called transpilation. The transpilation, it involves adapting the socket to match the physical constraints and topology of the target device while optimizing for its performance. One of the benefits of quantum computers are the advantage of its speed, the exponential speed of it gives. But in order to gain the exponential speed of our socket must be prepared in such a way that it will be compatible. It will be compatible with the targets, that the operations are compatible with the devices available, given the number of qubits and gates, which are essential for achieving the results of the computation. And to say this, there is this first, there are two forms of it. Like, when you write your operation, they have the basics operation, the likes of C nots, S gates, and Adamant gates. They are, yeah, basics operators of in quantum computing. But when you now have a combination of more of it, or a consume one, like we can talk of the likes of the parameterized sockets. So there comes the need in order to find a way of making them compatible with the program, the backend of the runtime, IBM runtime. Is done by using present or present pass manager. There's present pass manager. It helps to streamline the transpilation process. It configures the transformations. The transformation that will be done to our sockets in order to be conformable with the back end of the Qiskit IBM, which that's what it's called passes. It's called passes. When you write your sockets, it's written in the sequential order. This first operation will be performed before the other one. Are we together? This operation will be performed before the other one. It has to be once it has been written in that line. So it is sequential. It is in sequential order. When it is in sequential order, there's those sequential orders that are passes. That's when you have a socket that is being designed. You have that, okay, how many, that's when you can even talk of depth, the depth of the sockets, how many quick does it, how many operations does it, are we going to perform on it? You have to have the desired results. For example, just say now, you have your bits, you apply another gate to it, you apply C notes, you apply S gates in order to just get the measure, and then the final one, the measurements. You can see that it's in sequential order. It's not a password. And in making it easier for the user to optimize their socket without the need to understand on the underlying details. That's where the works of present pass managers does. Well, that's what it does. And in the process of breaking it down, optimizing the socket is called optimization, socket optimization, or optimization level. And we have three forms of it. We have optimization level at level 0. That one, nothing is being done. Like, you just leave the socket like that. And it ranges from 0 to 3. We have the optimization at level 1, as well as optimization at level 2, and optimization at level 3. I've said the baseline, which is optimization at level, nothing is being done. So you just pass the entire thing to the backend. This is the level that is primarily defined with characteristics of experiment. It maps the input socket to the target, but without performing optimization, ensuring that the socket adheres strictly to the hardware constraints. One of the limitation of the present NIST quantum computer, the near-term scales quantum computer, is like hardware issue. The hardware issue, like where it conforms. So in level 1, in level 0 optimization level, the socket is prepared. It's being transformed to a gates, the basis gates that are conformable with the hardware without optimizing the number of operation, without optimizing for the number of operation. That's why for this the first one is that which is optimization at level 1 is the default. In IBM Qiskit, or optimization at level 1 is the default settings. And it makes this transpiler makes a smarter decision regarding qubit mapping, and can combine or remove sequences of gates where possible in order to improve efficiency without extensive computational overhead. There are in quantum computers, in sockets, there are metrics. Yeah, there are metrics of measuring the socket performance. That's when you can think of socket, the cost, the number of the depth of it, the width, and no, the number of C notes that is being used. They are measured, and I think of recent I saw a measure of V is that was just really developed and published in one paper, like one article like that. That's, so those are the way they measured the sockets, or not just writing the gates, because the more complex the gate is, the more time it takes to run on a read hardware, in order to prevent that's where optimization level one will does. While optimization level two, it take an additional optimization techniques that are applied. It's take a notch higher, just a bit higher by on the sequence of gates, and ensure connectivities aiming for more optimal execution while still be relatively efficient in terms of time processing. Or the whole purpose of optimization is just to ensure that there is efficiencies in running of our sockets. Is first compatible with the transpiler we does it, but transpiler first, let me just to ensure that we are together. Transpiler does the work of converting our sockets, taking the socket, the operation in the sockets, and convert them to the basis gates that are compatible with the backend, with the topology of the backend of the IBM runtime, Qiskit IBM runtime. While optimization ensure that there is reduction of gates, reduction as where necessary in order to ensure efficiency, faster speed, to ensure that the speed is faster. Right, the last level is level 3. Right, it spends significant computational resources to improve socket performance, and it just takes more actions on it. Why the transpiler stages? Transpiler stages. We have 4 of them. We have 4 of them. We are going to look at together. We have the initial stage, the layout stage, the routing, and the translation. The initial stage is where you prepare your sockets. Prepare your sockets, unrolling consume instructions like parameterized sockets. We have done that in lab 2, where the likes of variational quantum sockets, VCQ, variational quantum socket. Those are custom sockets. They are not the basis ones, but they are custom ones. So in other one, it's the initial state is to convert them to the formats that is composed solely of 1 or 2 gates. It will convert them to a format that contains only the one gates. Like I can think of the basis gates like S gates, 2 gates. You can think of C nodes, control nodes, or control node gates, and the second stage, which is the layout stage. So in this stage, the virtual qubits in the sockets are mapped to the physical qubits of the backend. On the backend, it's marked with the physical qubits on the backend, and this map is crucial to ensure that the operations can be performed based on the device connectivities. It's ensure that there is connection between as described by the gate, as described by the prepared sockets. It's ensure that there is connection. There's connection. I don't know if you have listened to the likes of in optimization. We have we call something Johnson Johnson junction also, that ensure that there is a map, there is a connection between quantum sockets, so that it won't run on isolation. And this the third stage in compiler, the third stage is routing. After establishing the layouts in the second stage, this will inject necessary swap gates. It will inject necessary swap gates. You can just think of the like of swap gates of C nodes and control nodes, elements, and swap gates as necessary to change the other ones to be where necessary into the socket to ensure that the qubits can interact according to the backend connectivity constraints. The reason we need compiler is just because of the states of the backend of quantum at this present time. Yes, this is the NIST period. Yeah. So now I think we are Qiskit to utility scale, but at least there's an advancement, but the hardware constraint is still there. But at least a bit of progress has been made to link which quantum can be applied to the real world, could be at scale, utility scale. We can get benefit from using it. Okay, on that note, are we together? I just want to, are we together?
Yeah,
Yes.
we have achieved.
All right. Okay.
Yes.
Hope we get the other. All right. So I've actually literally runs through the. If you look at the outline itself, you're gonna see you've done a couple of things there. So as just a walkthrough, as Mr. Shedman has said, you're not the one that will be doing it, but you guys will be the ones to run through the exercises. So the first, if you look at it together, just we believe that you have had an experience in the first lab and the second one. So this is a continuation of it. Continuation of it. We have a setup. You got to install this the library, the necessary library. If you are using Google Colab, because it actually stated there, if you are using what's the name? If you are using a cloud-based ID, cloud-based, that's why you have to use these commands and you know, and these are percentage. I mean, and you store them. The first one, this kits visualization just for printing out the sockets. IBM runtime just to connect with the backend, Qiskit backend. Qiskit AER. That's a simulator, and we have the Qiskit transpiler service and the graphics. You passed your API. I believe you all have a Qiskit account. Pass it there. Yeah, import the necessary gates, the necessary library too, which is the final imports of random sockets, S gates, Y gate, which is their basis gates, and fake. The other one, which is the third library to import, fake provider. You can like is more of is an STL. I'll call it simulator. So this fake Torino, fake Osaka. There's real Osaka. This one is just a simulator of it. Simulator packing. Simulator. And we have our runtime sampler V2 and samplers. And we have to import a pass manager, which will be used for the transpilation process. We have to import generate pass managers, and why also for the visualization we need plot distribution, simulators, plugin, and that's I feel like I should run. Trying to run it too.
Sorry, we
Okay,
are not seeing
I've
that part you are
defined
running.
translation for it. It's the one it takes the
Hello,
input socket and map it to the topology and the
hello, can you hear me?
this space. Can you see this?
Hello.
Okay, yeah,
Okay, we
sorry.
can hear you, but
Sorry.
sorry,
I can hear you.
we can't see what you are running. Maybe you should scroll up.
Oh,
It's
it's
not
not moving.
moving.
It's not
Yeah,
moving as I'm going up.
yeah, it's not moving.
Oh,
You share
let
by
me
using the
stop sharing now.
entire screen. Click on share
Oh, all right.
windows, so you can just go to the
Oh,
browser.
okay, okay. All right. Sorry. Can we see the? Is it moving now,
Yes,
Mr.
yes.
Shegun? All right.
It's moving.
So okay. So this is the this initial. You have to install it. That's when you are using cloud-based. You are setting up the environment by installing all this. The necessary library. You have to first install it before you can import it. Before you can call it into your environment. Okay. So we'll use your API token. Sorry. Okay, Mr. Shegun. Sorry, I want to run the main, use my own. Okay, we have installed the necessary library now. So we want to, using of API token, I will quickly use my own air. I will quickly this. I don't want you guys to, but I think, okay, great. You want your API token. Okay, so we import the library, the random sockets, S gates, and the likes. Since we have installed the Qiskit library at the first, we just import the necessary thing we need. We import the great thing. Okay, transpiler. I've taken note to talking about it. Like, is the one just is a process of giving the taking a given input sockets and rewriting it to equivalent that is compatible with the specific address at the backend. And, the goal of the transpiler is to get best performance for noisy quantum, noisy intermittent scales era that we are now, NIST era that we are. We need a transpiler or a transpiler to go through. So we'll move forward. This is an example. This is it. Look at it. This example, this a little operation, this is a two-qubit operation that is being performed here now. This this is an example of, look at what transpiler does. Look at this. We have two qubits, qubits. Given a two-qubit like this now, we apply Adama gate to the first qubit. A control knots, a control knot where the first a Q1 is our controls and Q0 is our controls and Q1 is our targets. And we also apply another C knot to it after that, where Q1 is our control and Q naught is our target. Now, this simple operation that is being performed here, if you want to convert it to a back end, the one that will be compatible with the back end, the transpiler has to take it. You have to provide a socket that you have provided. You have to break it down to basis gates or instruction to basis gates to hardware to Qiskit IBM basic gates. Sorry. So it has to do a basic one, and you can just two, three operation that was performed. If you want to convert it to hardware specific, you have to convert it to a is the one that is being defined with many operation there. The central component of it is SDK and Qiskit's SDK. The transpiler is manage the whole neutral modularity and extensibility of it, with the main goal of writing a new socket that is conformable with the backend of the given backend. And this pipeline is determined by the pass manager and stage pass manager. The stage pass manager is a combination of many pass managers, many pass manager. Many pass manager as written, as you can see there. And the stages, there are 6 stages. The other one I mentioned 4, but actually the main stages, there are 6. The initial stage, where the initial passes are being run before embedding the socket into the system, which typically informing unrolling all the customs instructions and converting them to a single or two-qubit gates. By default, just to validate the socket instructions and multiple gates. Multiple gates, like CC not applying two control to it and not control not gates, and like three operation, like CC not control not gates. Control not gate, that's a 3-qubit one. It will have to be converted to it have to be break down. It has to be break down into 2 or single qubits. 2 or single qubits. And after that, the layout is being performed. Routing, we have to apply and inject swap gates. Swap gates, routing is just applying and injecting swap gates in order to ensure the backend connectivities. And that's the translation which transpire, we translate the gates and to the target backend basis gates, and optimization will ensure that there is removal of redundant gates, unnecessary repetition, where just to reduce the operation that will be performed and ensure optimal performance. So we have the exercise there. So for the exercise 1, let's go through it together. I'm not doing it, but just to go through it so that we can just have a glimpse. Okay, looking at, please match the description of what's happened in each stage with the corresponding translation stage names in the code cell below. A is a center stage around reducing the number of quantum of reducing the number of gates, socket operation, and depth of the sockets. Depth of socket with several optimization of options. And the second one, this stage is which is B. What B does? B does is a stage to execute the quantum in order to execute the sockets using the selected layouts. In order to using the selected layouts, in that layout, I actually intend to share something in the last IBM summer. It was IBM summer, because I want us to look at layouts. Sorry, let me just. Okay. So each of the backend has actually have a unique connectivities. I think if you can see what I'm showing, each of the IBM has like 5 or 6. I'm not we call it, or like 5 address backend like IBM Aero system, IBM Eagles, IBM Falcon system. Those ones are Falcon has been retired, but each one of them has their basis operators. I mean, basis gates or basis operator, and which is for the IBM Aero system, as we can see on the screen, is the like of CZ gates, rotational Z gates. You can have a square S gates, and you have S gates on it. For IBM Eagle system, we have the like of error correctional, ECR, rotational S gates, squared S gates. So each. Okay, these are the connectivities I'm saying about. Our kits or a qubit may have a limited connectivities. For IBM conducting hardware, this is limited to qubit that have physical connectivities. So the purpose of routing is to ensure there's connectivities in. As you can see in this, is an example of the retired Rochester 53 qubits gates. can see they are actually apart, but they are connected with one operator and the other. Like as you can see in this where my cursor is now, where my cursor is. So you can see it is at the like of IBM to Torano. Can see they are apart, but they are connected. They are connected. You know, and the purpose of connectivity is to ensure that our first the sockets, we need a number of qubits, a given number of qubits, a sufficient number of qubits for us to have a real world application of quantum computers. And and there is this when we have many qubits, there's a chance of there's this is called crosstalk. In order to ensure that there is no crosstalk, and that's why we have them being separated, like this, and but the likes of swap to ensure that there's connectivities between the numbers of gates that we have. Just a digression. So, so why for the day? This stage we execute a sequence of gates, one-on-one mapping of virtual qubits to a physical, the hardware at the back end that we have there. Why for E, for letter E, this pass can be thought of as explicitly inserting hardware aware operations like delay instruction to account for the idle time between the gate execution. I've said it. A gate doesn't run simultaneously. It's sequential one after the other. Also, in order to do this, we have been given an int just for this first example. The answer will always be a single. An int that we are given that the answer will always be a single capital letter with a quotation mark. For example, a quotation mark of A. So we have an answer there. I'm not meant to do it. We have an answer there like, okay, answers which ANS. We have a simple a dictionary, an empty dictionary there that has been specified. We are asked to place the correct letter next to the corresponding stage inside the parentheses. Corresponding stage, for example, text. Inside this parenthesis. So even looking at this now, for the initial state now, initial state is associated with what? We can type the answers. Just type the answer. The initial stage is can you hear me? I want us to do it. So I didn't want to do it for us, and that's the instruction.
I don't think the notebook has been sent to us.
Oh, okay.
The
Sorry,
notebook has
sorry.
not been sent to us. Yes, so
It hasn't been said. Okay. But they just want to put it together. I thought it has been so. Oh, that's true. It's only the first and
the second one.
second one. Okay. But in the interim, just let us want. I won't be doing it because I don't want to. Because there's a whether I will do it, but let's just want to do it together. I was thinking it was as the same. So we'll solve that one. After that, we'll pass. I know we'll have been familiar with. We submit our answer. Yeah, the grader will give us whether we get it right or not. Okay, okay, for to transpire with pass to put present pass manager, we need to explore Qiskit standard, which is the six. You can make, you remember the six approach, the six steps I mentioned the other time. The first one is initialize it. We can go back to it so that we can just have a refresh. We initialize it. We have a layout. We have a routing, transpilation, optimization, and scheduling. Initialize, layout, routing, translation, optimization, and what's the last one? Scheduling. Scheduling there. Okay, yeah, that's the six stages that we have there. And okay, those are it's an iterative process, the steps, it's the steps. Okay, looking at this now, we'll focus on the first predefined in this lab, we are going to focus on the first predefined transpiler pipeline and see how we can build a pass manager through a practice that uses the features and options of the pass with a predefined pipeline. In order to have an explicit knowledge, there's documentation, IBM documentation that we can use. Yeah, best we can look at it that we can look at what pass manager is and generate what generates present pass managers are. We can refer to as the IBM environment. Then let me something we can look at together. So actually, there is a documentation for it. There's a documentation for it, and this really spell it out with some sample of code. If you go to the GitHub environment, they give us a well detailed documentation. They have a well detailed with examples. Okay, what is a stage man pass manager? You know, a stage man pass manager or a pass manager, as I've said, it's an object that stores a list of transpiler passes and can execute them on the socket. We can create a pass manager by using the initializing words of using the word pass manager, where my cursor is. And there are list of transpiler passes options. There are list of transpiler passes. Is it at optimization as it at level 1, is it at level 2? Each has a different level of syntax. Why a stage pass manager is a class. You can just looking at like, okay, stage pass manager is a whole big circle. Why pass manager is a subset of it's a combination of many pass managers. That's why we have a stage. Is a class, is the one that houses it. It's a special kind of pass manager that represents the levels of level of abstractions that's of a that's above that of a normal pass manager. Why normal pass manager composed of several transpiler passes. A stage pass manager is composed of several separate pass manager. I've said it's a combination of one or two or more pass managers will make a stage pass manager. Okay, these in order to import this the library, you have to call the pass manager using the word Qiskit. In order to use this, you just have to use the word by calling the word Qiskit.transpiler dot calling the present pass manager itself. You call it as a function, and when it is being called, it's going to generate an instance. It's going to generate an instance. But when you have two more of it, that's when you can now you're going to generate an instance. When you have two or more of it, it's going to generate a stage pass managers, and it's going to execute. And you're going to define the optimization level you want to use. Optimization level, you know, I mentioned it's optimization level 0. You're not even doing anything to it. Level 1 is a bit. Level 2, depending on the task at hand. on the task at hand. And okay, we have a bonus exercise there. We have a bonus exercise there. So just gonna look at it together. Okay, let's look at optimization level. I've said it, in generate present pass manager function, it requires a position argument that you are going to add. Once you define this generate present pass manager, you are going to open a bracket. Like, if you are familiar with any Python or ML or this AI works, you are going to define, you are going to add an argument into it. In that argument, you are going to take whether it's level one, you define the optimization level. You can equate optimization level equals to, is it zero, that like no optimization at all? Is it the first one or second one? And there's a kind of a trade-off. Actually, there's a trade-off. That's it. High optimization level generates more optimized sockets at the expense of longer compile times. Are we together? There's a trade-off. The higher the optimization level, the more it takes to compile the sockets, the more it takes the compiler to which is converting them to the basis language, to the basis gates. To the basis gates. The more it takes, like having more of data, the more time it takes to train. That's just as an analogy, right? And we also have the utility function. Just let me run through. Utility function. Why? Since the goals of the transpilation is to improve the actual performance of the sockets, we have to provide a function that measures the performance of the socket, that measure the performance of the translated sockets. That's when you can benchmark. Then benchmark that, is it really doing the works? Does it reduce the amount of times? Does it optimize it? Does it reduce the gates? Does it, is the function really what, like, is the optimization really worth it? And we do that by using the function scoring, the word scoring. Well, we see the transpile sockets with final layouts, and it's target backend as the inputs, and it will return the socket score. It will return the socket, or there will be a metric which is the score function. The score function, it ranges from 0 up. The closer it is to 0, the more the better the transpiler the transpiler has optimized the socket itself. Why? Okay. Please use fake Torino for this whole lab. We are asked to use fake Torino. I think I said the other time that fake Torino is just it's actually a simulator that you can just liken it to simulator and know. Okay. Please other notes that's it. Okay, there is an example of optimization level 1 we have here. Okay, where you generate your pass manager. Optimization level 1. This optimization level 1 is intended for device characterization experimentation, just for experimenting. It only maps the input socket to the constraints of the backend without performing any optimization. It doesn't really have anything, and we do that by using the arguments, the position argument, the arguments in the layouts, by using what trivia layouts, from the word trivia, nothing really spectacular is being done. Just leave it as it is, and where it will just map the physical qubit to the backend, just add to the backend without optimizing the socket. So we have the likes. We can see that generate pass manager. You have defined your backend A. Let me show. We have defined our backend. At backend, we are using the backend of fake Torino. That's our backend that was specified earlier. We are linking it to the backend. Optimization level, said it, we have 0, 1, 2, 3. But in this one now, since it is optimization level 1, we are setting it to 0. Why? For seed transpiler, in order to ensure reproducibility, we have to set the seed. And the seed has been set earlier. The seed has been set earlier as 10,000, as been set earlier as 10,000. I believe we are getting it, and so we'll run as random sockets. Just like in it, there's no need to. You have to comment. For you to see to draw the circuit to draw the socket. You have to uncomment this. That you have to remove this and you run it. But when you just once you remove it and you run it, to run. Okay, why is for tax 2? That's it. For tax 2, find okay, for task 2 we have to find the depth of the sockets using the sum total to find the total gate number and compute the performance of the score. Before you can do that, you have to specify your gates, your backend, which we have specified earlier, and link them together. Why for the optimization level 1, that's when we are going to be looking at using the likes of light optimization. It's actually light optimization. It's not unlike the first attempt that is just a trivial one. This one, the first optimization level 1, it uses swap. It's apply swap in order to ensure connectivities between the qubits and with the minimum number of swap that is going to use that we're going to apply to it using Sabrim swap and VF2 layout pass post layout to try to select the best, the kind of optimization to optimize to select the best layout in order to have the best performance of the qubits. And okay, and why for the second one, the higher we go, the more the level of optimization it performs on it. The second optimization level 2 uses a medium optimization. It is done by using cumulative cancellation. And just in this example now, you just like you have in the first one, you are going to set your backend. You are going to define your password manager. You define it like generate using this term. This one that I like, generate password manager. You open the brackets. You specify your optimization level as is equals to 2. Sorry, I don't want to say it, but that's I think we can get it. And you set your seed transpiler into seed that has been defined earlier, and you remove these comments. Once you remove the comments, you run it, you get your answer. I think at these notes, let me just any question. Yeah, it's an interactive class. I want to hear from us from our side at least so far what we have learned and so far. Okay, any question, Mr. Adelowo Cornelius, Mr. Annie, and assume to be Mr. Any questions, sir? Oma?
No, no, sir.
No, sir. Okay.
No, sir. Not from my end.
Okay. But hope you get. Do you get the message? You get the workshop.
Yeah, I'm trying to follow though.
You're trying to follow.
I could have loved. I could have loved the fact that the notebook had been sent to us and we be doing it together. I guess that would have been a more like understanding from our parts. Like as you are doing it, we are doing it on our notebook too. But then we can actually come back to the
first attempt, because if you really want to get the knowledge, first attempt it. If it doesn't get it right, like that's when we can now come with okay, it should be done like this, should be done, there'll be learning in that process. Then if I just doing it like this, kind of I'm the one doing the workbook itself.
Mm-hmm.
And I actually, as Mr. Shegun has rightly said, quantum journey is not one time, it's a marathon, actually, that's it. And it's a kind of just so this is not lab, I'm just advising generally. It's a going of space, workspace, a going concept that is actually has a momentum. I think after AI is quantum that is next actually, and after AI, and quantum has the potential of evolutionizing, changing the way computing is being done, and it has a lot of potentials, popular potentials. And I'd advise this is Qiskit IBM. Is that after you have joined this, our advice you join if you are Nigerian, you join Q Nigeria. We have Q Community Nigeria can join, because learning is been like, it's good to, when you are learning a new thing, learning in a community where you can, community of like minds, people that knows the way out. They can ask questions, enumerate, and they'll be sharing of materials in order to facilitate your journey. So I'm just, it just of, this is not part of the lab, but just encouraging, kind of an encouragement. And I will also advise following up with mentor, the likes of Mr. Shegun. Mr. Shegun does he does he's member of, yes, the last time he was a mentor at Qiskit, I don't know at what keyword. And also we also have the likes, having a LinkedIn account. LinkedIn is also a good place to find, just ensure you follow people that are in that line of quantum. You're going to see different opportunities there, and the likes of open quantum communities, and that's it. On that note, I think we can call it a day if there is no question. Mr.
Sorry, please give me some
Mr.
minutes.
Shegun,
Give me some minutes.
Mr. Shegun.
You said we should give him some minutes.
Okay, okay. All right. So, well, let me share.
Okay, thank you very.
I have
Okay, you want to
some,
go? Yes.
Thank you very much. Sorry for not really participating. Something came up I need to sort out. And from there, I really appreciate Mr. Sam that took us today. So I want us to work on our exercise. This is just the last part. On Sunday, which is on 27th, that's when we issue certificates to those who submit their lab, and we are going to check it. Actually, some people will get certificate, but the main certificate will not be issued to those who did not participate with this on this lab. So I'll be so happy to invite most of us to that 27, whereby we will have just a chat. We talk randomly. We put us through the basic things that we need. Actually, there is a competition that is coming up. I got the mail. Please, I don't know if all of us can just open our. Sorry, let me just stop recording so I can share this thing out of record. So please